Here's the proof for Theorem 1. So let's walk our way through it. It says, for any input vector v in V, the vector space V, let its expression with respect to the basis be this. So vector is into, see the linear combination with respect to the basis vectors, the beta vectors. Then we're going to define the associated output by using the same coordinates. We're going to call this h of v. And so we're going to have c1, w1, so vector w1, all the way through c sub n and vector w sub n. And so this linear combination for the outputs, right? Now this is well defined because with respect to the basis, the representation of each domain vector v is unique. Okay, so it is well defined. This map is a homomorphism because it preserves linear combinations. I'm going to let you guys check that. Okay, so you should be able to check that. That it preserves, basically, preserves addition and scalar multiplication. So you can check that. Okay. In the proof, we normally will check that. I just don't have room, but I'll leave that up to you to check that it does indeed hold preserve linear combinations. This map is unique because if we have an h hat that has the same mapping, right? So let's call this mapping h hat is another homomorphism satisfying that h of hat of each of the beta vectors is equal to the w sub I vectors. Okay? For each I. Okay, then h and h hat have the same effect on all of the vectors in the domain. And I showed this, hopefully you can see that, but I took h hat of vector v, and so it's going to be h hat of the linear combination, right, of the beta vectors, because you can write v as a linear combination of the basis vectors. And so if we use the fact that it's a homomorphism, we can write it this way, and we can break it down into a sum of the h hats on each of the basis vectors. And then once we do that, then it's going to be h hat of the beta vectors, remember, is going to send us to the same thing because that's what we said it would do. It satisfies the same conditions. And so it's going to send all of the beta hats to the w vectors. And so now you're going to get a linear combination of the w vectors, but that's exactly what h does. So you end up with the same h of v. So you start with h hat of v and you end with h of v. So it has the same action, therefore it's the same function. Okay? And that is the proof. Have a great day.